Today we are talking about refraction and the Snell law. Let's first look at these two images. Both images show some trees inside water, but obviously we know the left one, there is nothing in the water. What we see is just a reflection from the tree above the water to the human eye. And in this reflection, we know that the incident angle and the reflecting angle, they are exactly the same, follow this miniLecture symmetry. However, on the right side, where we see the tree inside water, it's indeed a tree inside water. What happens is the light coming from the water has slightly bended effect when it comes out to the air. That's why this tree looks a little bit weird. It doesn't really follow the way the tree should glow in the water. If you have experience trying to catch some fish in the water, you will know that if you go with what you see in the water, you are likely to be fail. You have to consider what you see, it's a little bit bent inside water. And this behavior, light transfer from one medium to another one with a slightly bent angle is called refraction. And this geometry does not matter, the light comes from air to water or light comes from water to air. They follow a similar geometry. Maybe at the beginning it will be a little bit hard to remember in which angle does this light bend. So perhaps this way will help you to understand this behavior a little bit easier. We can imagine the light transfer in air as a car driving on a highway. And when the car reaches the water, it's like reaching a muddy land. And the right front wheel will slow down. And we know that when the right front wheel slows down, the car will start to rotate towards the right side. And they keep driving in after it rotates. So this is just like a general feel for you to maybe remember this effect better. And since light transfer in different medium with different speeds, in optical physics, we use this reflective index n to describe this property of different media. For instance, the speed of light in vacuum is c, and the speed of light in water is phi, and then the speed of light in water is smaller than c. We get a reflective index larger than 1 for water, which is 1.33. And for other medium, when the light transfer even slower, we get an even larger reflective index. And this index angle and this incidence angle and the reflection angle, also the speed of light in different medium, they follow certain law, which is called the Snell law. Obviously, it's founded by a scientist called Snell. He's a Dutch person. And if it follows the mathematical equation as if the speed of light in medium 1 divided by the sine of the incident angle is equal to the speed of light phi 2 divided by sine of theta 2. Theta 2 is the reflection angle. Or if we use the reflective index we just learned earlier, the n value, we can derive this Snell law. We can describe this Snell law in a different way, like the equation on the right side. And now how to derive Snell law? There are several ways we can do that. One way is by using the Fermat's principle. Fermat's principle told us if a beam of light transfers from point A to B, it does so along the fastest path possible. So imagine there's only one medium, the light will transfer along a straight line because that's the shortest route. However, now we have air and water, and light transfer faster in air and slower in water. What will happen is that the light will stay in air longer than in water, like this, and eventually find a best point that the total time will be the shortest. Then we can get all these out by geometry calculation. We have constant value A and B, and X and Y are changing because the junction point is moving left or right, try to find the best position. But the sum of X and Y is also constant. Then we can express the time we need at air by T1, by the distance divided the speeds, and the same thing for T2, the time we need in water, the distance divided by the speed of light in water. When we add them together, what we need now is a calculus. We try to find the stagnation points to get the shortest time. If you are interested in mathematics, you can do it yourself. I did it for you here. And look at what we get now. What is inside this orange box is basically sin theta 1. If we look at the value in the blue box, it's basically sin theta 2. So when this stagnation point is reached, we get this equation, which is Snell law. So we derive Snell law successfully. Now we understand Snell law. What are the consequences of it? For instance, if we look at something coming out from water, there are actually two things happening at the same time. The light is reflected back into the water, and meanwhile, some light will come out from water to the air. So we have both reflection and refraction in the same time. And because the light transfers faster in air, we have a larger angle theta 1 than theta 2. If we increase theta 2, if we are looking at things more shallow, then theta 1 will also increase in the meantime. If we keep increasing theta 2, to a certain point, theta 1 will reach the maximum, which is 90 degrees. And then this angle theta 2, now it's called the critical angle. We describe as theta c. It's critical because once the lights keep increasing the theta, things become more shallow in water, no light will escape from water because we don't have an angle larger than 90 degrees for theta 1. All the light will be reflected inside water. We know the reflection index for water is 1.33, and we know Snell law now. We can calculate what is theta c. We put this value into Snell law, we get theta c is equal to 48.8 degrees. Anything above 48.8 degrees from water is not going to come out. We're not going to see it. Now, if we look back at this imaging, we will understand why at further place we don't see anything in the water, but in a closer distance we see those trees coming out, the light coming out, and we can see what happened there. There are other consequences of the Snell law. So, for instance, like optical fiber, I follow the same thing. We are basically using the critical angle behavior. If you have a laser point and a glass load, or in this case, in this example, is a quarry load, you can try this yourself. You change the angle of the laser point, and to a certain point, you'll find no light will escape from this load, glass load. Everything will be transferred, reflect inside the load. And that's exactly the principle of optical fiber. In this way, no light will be escaped and no information will be missing. That's why optical fiber usually is much more efficient in transferring information. Now perhaps you can calculate the critical angle needed for the glass and air reflection to reach this behavior. And after you calculate the value, you can compare with what you observe in experimental and see if they fit with each other. There are other consequences of Snell law. For instance, like this dispersion. When we talk about light, we assume light is a simple object, but it's not, because light is formed by different light with different wavelengths. The white light come from sun. So, for instance, we have red light with larger wavelengths than the blue light. They travel in the same speed in vacuum, but this is not true anymore when they come to other media like water. In water, the red light has a smaller reflective index than the blue light. And in air, the N1 and the theta 1 is the same. For both of them, we can again use the Snell law. Since N red is smaller than N blue, the theta 2 for red light will be larger. That's why the red light has a wider reflection angle than the blue light. The blue light is bent more than the red light. And now imagine we have all different wavelengths. What we get is a continuous dispersion of different light with different wavelengths. That is what we see in this beautiful rainbow. And also we can intentionally use this phenomena. We can use prism to separate light with different wavelengths. And now again come to extend thinking. Perhaps you can find some other example of the application of Snell law and maybe explain how do they work. That's about Snell law and reflection, and I look forward for discussing with you.